of quantum. Raise your hand if you traveled by plane to get here. Most of you, as expected. Did anyone fly from Boston? Okay, I also flew from Boston. Did you know that US flights consume 1 to 2% of the entire world's energy supply? Do you know what else consumes 1 to 2% of the entire world's energy supply? It might not be what you would expect. The answer is the production of fertilizers. Fertilizers are used to enhance the growth of plants, which we use to make food. Fertilizers are made from ammonia, and ammonia is produced by a process that takes place at extremely high temperatures and pressures. I am going to show you how quantum computers could help us solve this problem. We know in nature there is a substance that can produce ammonia at room temperature. So if we could just understand how this substance works, we could make a more efficient process to produce ammonia, and therefore fertilizers, and therefore more food at a lower energy cost. So the primary molecule in the substance looks like this. It's not that complicated. So we could simulate it on a computer. How could we simulate it? Well, computers store and process information in bits, zeros and ones. So how many bits would it take to simulate that molecule? Anyone think? It would take 10 to the power of 32 bits. That's 1 with 32 zeros after it. That's a really large number. What can we compare this to? Well, I heard there are about 40,000 people at this conference. So take the number of atoms in one person and multiply it by all the people at this conference, and we will get the number of atoms in all the people at this conference. And that is 10 to the power of 32. But what about quantum computers? How many quantum bits would this task require? Quantum bits are the analog of bits. Can you guess a number? Okay, yes. It would take just 108 quantum bits. So to summarize, on a classical computer, known as the computers we have today, the number of bits you would need is more than the number of atoms in all the people at this conference. But on a quantum computer, the number of quantum bits you would need is fewer than the number of people in this room. And later in this talk, we'll see why this is the case. There are many other examples of molecules that we cannot efficiently simulate, and that is because nature doesn't work by bits, zeros, and ones. Instead, nature is quantum mechanical. So it makes sense to use a quantum system, such as a quantum computer, to simulate a quantum system, which nature is. So one potential application of quantum computers is to simulate chemistry, which could help us save some of the world's energy. There are multiple steps to make quantum computers useful. In this talk, I'm going to walk you through each of these steps. First of all, we'll look at potential applications in a variety of fields. Then we'll look at a couple of quantum algorithms and how they can outperform our current computers' algorithms. Then we'll look at quantum bits and what makes them so special. We'll look at how you can build quantum circuits from these quantum bits. And then we'll look at how you can physically build a quantum computer. Finally, we'll look at the research, where we are now and where we hope to be. So let's start off with the applications. So if we could simulate chemistry, then we could potentially discover new medicines, which could cure some diseases. We could design new materials, which can make the devices you use on a daily basis better. Machine learning deals with vectors in high-dimensional real space. And quantum mechanics deals with vectors in high-dimensional complex space. So you can actually map the two together. Therefore, quantum computers could be used to advance artificial intelligence. We have made progress in AI now because of the more powerful computers we have today compared to many years ago. In a similar way, there could be a new wave of progress in AI if we are able to use quantum computers. So researchers, like myself, have already been working on such applications in chemistry and in AI. But there are more speculative applications. For example, you could improve optimizations and analysis in the financial industry. You could find best solutions for logistics and global supply chain problems, which could lead to more efficient travel for you. We could accelerate space exploration by improving navigation systems. With quantum computers, we could solve problems that are not currently possible in our lifetime with today's computers. So how are we able to get all of these amazing applications? That is because researchers have come up with quantum algorithms. Quantum algorithms are a set of instructions that you give to a quantum computer. And some of these quantum algorithms can outperform classical algorithms. So let's take a look at some examples. One task is called integer factorization. This basically says, what are the two numbers I can multiply to give me a certain number? In this case, it's easy for a computer to know that 5 and 3 multiply to give 15. But it's really, really hard to know what two numbers you must multiply to get the 617-digit number. In fact, so hard that it could take 1 billion years using the best-known algorithms on our current computers. And encryption uses this hard problem, so your internet data is secure because of such a hard problem. But what about quantum computers? How long could it take to find those two numbers? Anyone want to guess? Yes, it could take just 100 seconds. And we can do this using a quantum algorithm called Shor's algorithm. So quantum computers could break most of the encryption methods we have today. But it hasn't happened because in order to do that, we need a large-scale quantum computer. And currently, no one has built that. Also, people are working on post-quantum cryptography. These are methods that could be potentially safe against quantum computers. But this shows the power of these quantum algorithms. So far, we've seen that we can simulate chemistry and perform integer factorization significantly faster on a quantum computer. Why are we able to do this? Well, that's because there are a certain set of problems in the world that take significantly longer as the size of the problem increases. For example, imagine if you had to enter one digit on your phone for your passcode. That would be extremely easy to crack. That would take, at most, 10 tries. But if you had to enter 4 digits, then that's harder. That would take 10,000 tries. And now you have to enter 6 digits on the iPhone. And that takes, at most, 1 million tries. So this is what the problem looks like. The time to solve it scales exponentially as the size of the problem increases. And the blue curve shows how long it would take on a classical computer, the computers we have today, our normal computers. And this is the advantage that quantum computers could give you. The orange curve shows how long it would take to solve as the size of the problem increases. But not all problems in the world scale exponentially. For example, if you had one number, one digit, that obviously takes 1 try. 4 numbers, that would take 4 tries. 6 numbers, that would take 6 tries. So this problem scales linearly as the size of the problem increases. But quantum computers can give us an advantage there too. And these are the bottom 2 curves zoomed in. So let's take a look at such an example. The task is searching an unsorted database. So if you want to do that on a normal computer, then I have an illustration. So let's say that I want to find the ball 7. So each of these balls has a unique number from 1 to 100. And if it's completely unsorted, then what a normal computer has to do is it has to look at a number, check whether it's the number 7, then discard it. Then it goes to the next one, checks whether it is the number 7, discards it. And it continues to do this until it finds the number. So how many tries would this take at most? It would take at most 100 tries. But how many do you think it could take on a quantum computer? Anyone? It could take 8 tries. And later in this talk, I will show you how it's able to do that. So to summarize, on a classical computer, the computers we have today, it would take at most n tries with a database of n entries to find a particular entry. But on a quantum computer, you could do it in at most square root of n time. And we can do this using an algorithm called Grover's search. And later in this talk, we'll see how this works. So how are we able to get these quantum algorithms that can outperform classical algorithms for a particular task? That is because these quantum algorithms use quantum bits. What exactly is a quantum bit? A quantum bit follows the laws of quantum mechanics. Quantum mechanics describes how the world works at the most fundamental level, the level of atoms and subatomic particles such as electrons. For example, when light hits this plant and converts it to chemical energy, that whole process can be explained using quantum mechanics. There are 2 main principles of quantum mechanics that quantum computers use. The first one is superposition, and the second one is entanglement. So in order to understand how quantum bits work, let's first understand the classical bits. Classical bits can be either 0 or 1, and these are just 2 states. It can be any 2 states. For example, the 2 states of this donut. We have the frosted side, and we have the plain side. So we can say the frosted side is 1, and the plain side is 0. But quantum computers use quantum bits, which are different at the fundamental level. They can be 1, they can be 0, but they can also be a superposition of 0 and 1. What is a superposition? It's like a spinning donut. When it is spinning, it is neither on its frosted side, and it's neither on its plain side. In fact, when it's spinning, it has a 50% probability of landing on its plain side when it stops spinning, and a 50% probability of landing on its frosted side. And this is important because this superposition only happens when I am not observing it. If I decide to make a measurement, I actually force it to stop spinning, and it will either land on its plain side or its frosted side. And this is important because remember that information is just a sequence of bits. So to make quantum computers useful, we need to be able to measure the system, so we measure a sequence of bits. But if we have 50% probabilities, that's not very helpful because it would just give us a random answer. So you can actually change the probabilities of each state of the quantum bit. For example, you could have 60% 1, 40% 0, or any range of probabilities. And then what we can do is we can do multiple measurements. So in this case, if we have 10 spinning donuts, and each donut has a 90% probability of landing on its frosted side and a 10% probability of landing on its plain side, then when we make a measurement, we should expect that 9 of them will land on their frosted side and 1 will land on its plain side. So how do we change these probabilities? Well, there's a special number that each state has called the amplitude. The amplitude can be positive, it can be negative, and it can even be a complex number. You can imagine the amplitude like the height of a wave. And this amplitude is related to the probability. If you take the modulus squared of the amplitude, you get the probability. And so quantum bits have an amplitude associated with them. And what you can do is these quantum bits can actually interfere with each other. So let's say if we have 2 waves and they add together to give us a new wave with a higher amplitude, then we call that constructive interference. If we have 2 waves that cancel each other out, and so we get a new wave with a lower amplitude, we call that destructive interference. And so what you want to do in quantum computers is you want the paths to the right answers to constructively interfere so that they have a higher amplitude of measuring the right answer. And so you have a higher amplitude of the right answer, and therefore a higher probability of measuring the right answer. And then you want the paths to the wrong answers to destructively interfere so that you have a lower amplitude of getting the wrong answer and a lower amplitude of getting a lower probability of getting the wrong answers. And so now we can understand why simulating chemistry is so hard. If I have two classical bits, then it can be in only one of these states at a given time. So plain plain, frosted plain, plain frosted, or frosted frosted. But if I have two quantum bits, then it can actually be in the superposition of all of these states. And in this case, it has an equal probability of being in one of those states. But those probabilities don't have to be equal. So if I have two classical bits, obviously I get 2 bits of information. But if I have two quantum bits, in a sense, I get 4 bits of information to a certain precision, because those probabilities are extra bits of information. If I have 3 classical bits, I get 3 bits of information. But if I have 3 quantum bits, it can be in a superposition of all of those states, so we actually can get 8 bits of information. So we can summarize that to represent a state of n quantum bits, you would need 2 to the power of n classical bits of information. And this is why simulating that molecule was so hard, because it would require 108 quantum bits, but it would require 2 to the power of 108, which is roughly 10 to the power of 32 bits on a classical computer. And so the second quantum principle we can use is called entanglement. In order to illustrate this, let's say that I have 2 boxes. And in each of the boxes, we have a ball 1, 0 in the pink box and balls 1, 0 in the blue box. Then, if I shake up these boxes and I randomly draw out 1 ball from each box, for example, 1, 0, you can see that we have a 25% probability of getting each of these states. But if I entangle the boxes, then the probabilities will actually be different. We could get a 50% probability of getting 1, 1, and a 50% probability of getting 0, 0, and a 0% probability of getting the other states. So if I pick out the ball blue 1, then I know that the pink ball must be 1, because it has a 0% probability of being 1, 0. And so if we have two entangled quantum bits, you would get a state that looks like this. It has a 50% probability of being plain plain, and a 50% probability of being frosted frosted, and a 0% probability of being in the other ones. And then what happens is we can use superposition and entanglement in special ways to create those quantum algorithms that can give us the advantages. So let's understand how we can use superposition and entanglement in special ways. So we need to be able to build quantum circuits to do that. So in order to build a quantum circuit, let's understand the different things that we can do to our quantum bit. The first thing we can do is make it go into superposition. We can also entangle 2 quantum bits together. We can also do something called a bit flip. This basically says, if I have a donut that's frosted, then I can flip it to the other side. So 1 goes to 0, and 0 goes to 1. And we can also do a measurement, which forces it to stop spinning. So we use quantum gates to perform each of these operations. And what I will show you is I will show you all of the quantum gates in order to make this algorithm possible. And so when we have quantum gates, we can put them together to create quantum circuits. And then in order to implement quantum algorithms, we can use these quantum circuits. So let's understand the first gate. So the first gate is called the Hadamard gate. Basically, what this says is, if I have a donut that's either frosted or plain, and then I put it through the Hadamard gate, then it actually ends up spinning. So this puts it into superposition. I can also have something called a C0 gate. This says if I have two quantum bits, I can put them through the C0 gate, and it will end up entangling them together. We can also do the bit flip. This basically says that if it's plain or frosted, so in this case, if it's plain, and I put it through the gate, then it actually flips it to the other side. So now it's frosted. And then the last thing we can do is a measurement. This basically says if it's in superposition, so it's spinning, when I put it through the measurement device, it will actually end up start spinning, and I will either measure frosted or plain. So we can put multiple of these quantum gates together to create a quantum circuit. This is a simple quantum circuit that demonstrates superposition. We have a donut that is in the frosted state. It goes through the gate to put it into superposition, so it starts spinning. And then we put it through the measurement device, which makes it land either on its frosted or its plain side. And we can run this 1,000 times. And if we run this 1,000 times, then we should expect 500 times to get the plain donut at the end, and 500 times to get the frosted donut at the end. And you can actually try this on a real quantum computer. The session after this, Jerry will show you how you can run this stuff on a real quantum computer. And so, now you understand how we can implement the algorithm for Grover's search. Remember, this is the one that can search through an unsorted database in square root of n time. This is a more complicated quantum circuit, but you actually know now all the gates in order to implement this algorithm. So we can go through each of these steps. So the first step, so let's say to simplify the problem, I have 4 balls, in this case numbered from 0 to 3. Then I want to find the ball number 3. Well, on a classical computer, that would take at most 4 tries. In this case, it would take it would take at most 4 tries. But on a quantum computer, it can take at most 1 try. So in order to actually implement this on a quantum computer, we have to convert the numbers to bits. So in this case, we convert each of these numbers to bits. So that means that I only need 2 quantum bits to implement this algorithm. So we want to find 1, 1. So the first step to do this is the superposition. So you can see the Hadamard gates. What this does is, remember, it puts them, in this case, the Hadamard gates puts it into equal probabilities. So they have an equal amplitude of all occurring. Then the second step is called an oracle. Basically, this quantum circuit is designed to find the number 3. So what this does is it makes the amplitude of the ball number 3 negative. And this is where the fact that the amplitude's negative is powerful. And then step 3 is called a reflection. So what this does is it basically finds the average of the amplitudes, in this case the dotted line, and then we find the mirror of each of the amplitudes of the balls. So the blue balls in this case is the reflection. And then we end up with something like this. And the fourth step is measurement. So we actually need to measure our system to get a sequence of bits. So in this case, remember that the modulus squared of the amplitude is the probability. So if we have a 0 amplitude, we have a 0% probability. But if we have an amplitude of 1, then we have a 100% probability. So when we measure it, we have a 100% probability of getting the answer 3. And it can do that in just 1 try. So as you can see, these quantum algorithms use superposition and entanglement in special ways to give us the quantum advantages. So now we're going to look at how do we actually run these quantum algorithms? Well, we need to build a quantum computer. And how do we build one? Well, to understand that, let's understand how we build our normal computers. Computers, as we know, have bits 0s and 1s, so we need a way to represent these 0s and 1s. Computers use transistors to do this. They basically block and allow the flow of electrons, which can act as the 0s and 1s. And then you can do more complicated things and get chips, which make our computers. But it didn't always used to be that way. In the early computing days, people actually used vacuum tubes instead of transistors. Transistors ended up being cheaper, easier to scale, and more reliable, so that's why we use them today. But in a similar way to the early computing days, in the early quantum computing days, which is now, by the way, there are actually multiple ways to build a quantum computer. So in order to build a quantum computer, you need something that can be a quantum bit. It needs to be 1 and 0, but also a superposition of 0 and 1. And so how can we do that? Well, there's actually multiple ways to do that. Researchers have used superconductors. They've used trapped ions, which are atoms with a net electric charge confined in a space. They've used photons, and they've even used diamonds. So as you can see, there are multiple ways to build a quantum bit, and therefore multiple ways to build a quantum computer. So companies and institutions are working on these different ways, and are trying to find the most reliable, scalable way. You can see that one challenge of building these quantum bits is to maintain the quantum effects. Just like the spinning donut, it's hard to keep it spinning forever, because forces from the environment will stop it spinning. In a similar way, forces from the environment can destroy the quantum effects of these quantum bits. And when you have multiple of them, it's even harder. But despite that, rapid progress has been made in the hardware space. Just a couple of years ago, we had a quantum computer with 5 quantum bits, and now we have a quantum computer with around 50 quantum bits. So even though you can't buy a quantum computer, you can actually still use one. And so IBM released their quantum computer on the cloud called the IBM Q Experience. And right now, there's a class at Harvard called Engineering Quantum Mechanics that uses this quantum computer to teach the students. Researchers are using quantum computers to run their experiments and algorithms. People have even built quantum games using these quantum computers. So now we can look at the research, where we are and where we hope to be. So there are 2 parts to the research. The first part is the experimental part. This looks at how can we build these quantum bits, and how can we actually build a quantum computer. And we've seen different ways to do that. The other part is sort of the theory and applications. This looks at how can we build these quantum algorithms, such as this one, and how can we apply it to a variety of fields. So in the hardware space, we've seen that in the past we had 5 quantum bits. Currently, we have around 50 quantum bits. And in the future, our goal is to get to a large-scale quantum computer. This would be a quantum computer with millions of quantum bits. In the algorithm space, we've already designed algorithms such as Shor's and Grover's that can give us the quantum advantages. Right now, people are also working on such algorithms, but they're also working on something called hybrid quantum classical. These are algorithms that can basically use both classical computers and quantum computers. So you use them both to perform a particular task. And in the future, we hope to come up with new algorithms. So we have seen that in order to run Shor's algorithm, for example, the one that could break encryption, we need something like a large-scale quantum computer. But there's been a new effort in research to actually try and build algorithms that can be used with our current computers. So this is how you are able to get to all of these amazing applications of quantum computers. We've seen that we could solve certain problems much faster than today's computers. We could understand nature more accurately. We could discover new medicines, and we could advance AI. There are 2 future states of the universe, one with a large-scale quantum computer and one without a large-scale quantum computer. Right now, we're in a superposition of both. Who knows what the probabilities are? But as researchers, our goal is to increase the probability of the large-scale quantum computer side of the donut so that we have a higher probability of landing on that side and a higher probability of a quantum future. Thank you.